main organizer for this. I mean, we did a workshop similar to this 2 years ago, and she was the leader of that, and so I'll say thank you to Linda for inviting me back to be a part of this. And it's great to have all of you here, and I'd like to welcome you all as well, just like Linda did, and Jim did, and Chris has done. And you'll hear that a lot today, probably. So this is my introduction to who I am and what my interests are in the workshop. And so who am I? Well, this is a picture of me at the last uncertainty workshop up in the mountains in Rocky Mountain National Park. And so it looks like I have a little bit of a paunch there, but I swear that's not quite as true to the picture. So who am I? So this is the A-list mashup. How many people know what a mashup is? Excellent. Okay. I expected more people here as to what that is. Talk to me later about it because I don't have a lot of time. But first of all, in my context, the A-list mashup is what I consider myself to be my main attributes. One, I'm a physics and math junkie. I didn't say nerd this time as I did last time. I am a professor of climate dynamics and meteorology at Penn State. And you'll see that's the first use of the hashtag here. So if you're watching these things. Another one is that I'm a co-PI of the Network for Sustainable Climate Risk Management, which is one of the co-sponsors of this group. And so a number of you I look forward to meeting who are here as part of the SCRIM network. I'm also a pragmatist and a realist when it comes to the decision-making questions that we're talking about this week and for the next 2.5 weeks. And so we always talk about quantifying things to high precision for probability distributions of future climate change or parameters in our models or things like this. But at the end of the day, we need lots of extra information in order to actually make real world decisions. And so I come at the problem of I'm only supplying one part, and that's I think how I fit into this uncertainty workshop quite well. The other one is I'm a hiker, a biker, an outdoor guy, and I'm a dad. And I don't have a picture of my 2 boys and my wife who are out in the mountains for this week, but they'll be here at the remainder of the week starting next Thursday. So they'll be here for the last week of the workshop, and I hope you get to meet all of them. But that means that I'm also interested in the future for my boys, and so I wanted to make sure that we have a vested interest in leaving the planet a better place as a result of all of the things that we're doing to it at the moment. The other is I'm putting on here my Twitter feed. How many people have you used Twitter? Excellent. Okay. Ooh, hey, did you sign up last night, Haley? Oh. 2 weeks ago. All right. So that's my Twitter account. Please use it. We were talking about creating a hashtag for the event. We don't actually have a Twitter feed for the ASB colloquium, and I was talking with Chris about this, and this is just something that's not commonly done here, so that's just fine. So what we should do is create a hashtag for the event, and I wrote one down over here. So my pen's dying on me, that's not good. Underscore. Can you read that? No. All right.
Oh, I can see that.
Awesome. Is that good? All right. We'll see the buzz, the trending on Google or on the Twitter feed right at the moment. We were going to put IU, but then Chris told me that that's the initials for Indiana University, and I thought that's probably not a good idea. So we'll put that down there. The other one is I'm on Google+. I tend not to use Facebook for professional things, so I separate Google+ from my Facebook page. And the other was I'm on LinkedIn, and a few of you have already asked me to join on LinkedIn, and please remind me of that, because I didn't know who you were until when I got these invitations. So just so you're aware of if I didn't respond to you properly quite yet. Now, how many minutes have I used up? Just getting through that. 4. Excellent. Okay, I'm speaking quickly. Good. All right, so what are my goals for this workshop? For this talk, I want to briefly introduce uncertainty language, and I'm definitely doing it briefly. And I want to also introduce some things that we know about climate change. Linda already introduced the Keeling curve, the iconic curve, which is actually on the first object to leave the solar system. Has a picture of the Keeling curve on it. What's the name of the spaceship that went out there? It's part of a Star Trek movie. Voyager, right? Voyager 1. For this workshop, I want to teach and be taught by your cohort. I'm not calling you a generation. We talked about this last night, but I think you guys are going to be a group which is going to move forward through your careers together. And already, Jim and Chris Jim Hurl and Chris Davis alluded to what the ASP Colloquium is about. And so I want to learn about your research, your interests, your backgrounds, your excitement of those things that are going to lead us into the next generation of climate science driven by an understanding of uncertainty. And for me, my research, which is what I'm learning from you guys, is how do we characterize and communicate the risks of climate change. And that tends to be the summary statement of the things that I do in my general research agendas that I have. As you saw, I was a physics and math undergraduate. I got a degree in meteorology for my PhD, and then I've worked in the policy area in addition to the basic climate science area for the last almost 2 decades now, it seems. Okay, so what does this talk about? 1, introducing the language of uncertainty, and 2, introducing some certainty about climate change as to what, and we'll obviously look at that and see what that means. So types of uncertainty. Linda discussed the issue of aleatoric uncertainty versus epistemic uncertainty. And those are 2 key words. If you don't know what they are, look them up. That's what we have Google definitions for, I guess. So we can use that. The types of things that we're going to talk about here in the next couple of weeks are going to be the differences between structural uncertainty and parametric uncertainty. We'll talk a lot about these sorts of issues. Starting to see a few head nods. Yes, now I start to see something that makes sense to me. This is good. Structural uncertainty tends to be what's embedded in the structure of a model as you build it. So we can talk about statistical models. We can talk about numerical prediction models. Once you build that model, you are encoding in that very specific decisions about what's important for the predictions that you're going to make with that model. And within that model, you're going to have parameters which are going to be controlling the response of that system, and those parameters are then uncertain, and those are then going to contribute to the uncertainty of the model that you've for the future predictions as well. I also included the aleatoric and epistemic types of uncertainty. Aleatoric is randomness. Epistemic is our basic understanding of the knowledge, and Linda went over that already. Another one is deterministic versus stochastic. Because we're dealing with the climate system, we have a set of equations which are governing the models of future climate. And those models, in mathematical terms, have chaotic equations. They show internal variability, which is just driven solely by the interactions between the equations of motion and the equations of energy balance and so on and so forth. And that's fairly different than sort of a stochastic process where something is essentially purely random. We think of the weather at one level as being purely random, but in fact it has a chaotic component or a nonlinear dynamical component to it. And so separating out what is the deterministic component from the stochastic component is another way of trying to separate out the different types of uncertainty. And then there's this last one, which is what we consider to be quantifiable uncertainty versus non-quantifiable uncertainty. Quantifiable are things that you can go out and measure, or you can write down models for parts of the climate system. And we can go about asking what are the values of the parameters, or what are the values of the uncertainty ranges for the predictions of climate out into the future. But that doesn't necessarily tell us something about the risks that are associated with societal changes. The way in which the future evolves is going to have some component which has nothing to do with numbers, probably. It's going to have everything to do with the way we learn to interact with the environment or with each other, and how the world is going to behave over the next 100 years, or well out into the future. And those types of features I would consider to be non-quantifiable, and that's an aspect of how we treat the uncertainty problem. Okay, I want to take a few moments to talk about modeling uncertainty, and I raised the issue of structural uncertainty versus parametric uncertainty here at the beginning. And so one of the issues is, how do we actually go about characterizing the uncertainty in the climate models that we have? This is one of the things which is most near and dear to my research agenda, and so I think it's worthwhile talking about the different types of ensembles that we have available to us to talk about the range of uncertainty in climate predictions. One of them is the multi-model ensembles. We have about 25 to 30 groups around the world which are building state-of-the-art climate models, and each one of them is producing their best estimate. Their best estimate of how the world is behaving and how it's going to be going forward into the future. But that doesn't necessarily capture the range of all possible models. The collection of best models is not the same thing as the models which are considered to be consistent with the way the world works. Some of these things might be familiar with you, some of them might not, and so I think it's good to get this language out front right away. So another way of trying to sampling the uncertainty of the future predictions in climate models is through what are called perturbed parameter or perturbed physics ensembles. And this is more like trying to understand the parametric uncertainty associated with a specific model. If we have, for example, the way the clouds behave in the atmosphere is a big component of the uncertainty in future climate predictions. And we have multiple parameters in our climate model, which are going to be which are uncertain, and we can go in and we can tweak these parameters and look at the way in which the model responds, and we wind up then with a set of model simulations, which are then creating an ensemble where the parameters have been perturbed. I have 5 minutes left. Okay. So perturbed parameter or perturbed physics ensemble is something that we'll talk about a lot tomorrow. The last one is this initial condition ensembles, where we know and recognize that there is this uncertainty associated with our basic understanding of the current state of the climate system. Just like we have weather predictions, which are uncertain to our understanding of the winds, the temperature, and humidity distributions in the atmosphere. We have a set of initial conditions that are consistent with our understanding of the current state of the system. We sample from that uncertainty to create an initial condition ensemble, and this is one more way of probing the uncertainty of how the models are responding to the future. Another way of talking about this through the multi-model ensemble approach is something we call model intercomparison projects, where we try and understand the basic, the goal of this is to assess the structural uncertainty due to model structure and experimental design. And the first of these intercomparison projects was done in the late 1980s, and it was called the Atmospheric Model Intercomparison Project. And what they were doing was comparing the way in which different feedbacks in the climate system are different among the various atmospheric general circulation models at the time. Since that time, and we'll talk more about this tomorrow. But since that time, there have been a huge collection of model intercomparison projects where these expert groups around the world provide a very specific experiment that everybody runs, and then they look at the outputs and ask, why are our models different from each other when it comes to the climate model predictions. And so the second of these was the Coupled Model Intercomparison Project, CMIP. And this was they included the ocean component of the climate system in this one to call it a coupled model. And we're now up to version 6. We had CMIP 1, 2, 3, we skipped 4. We had CMIP 5, which contributed to the latest IPCC fifth assessment report. And now we're talking about the 6th set of coupled model intercomparison projects, CMIP 6, and this is now moving on. We'll hear a lot more about other intercomparison projects. There are many more, and this is the 3 that I have here at the bottom are a very, very small sample. One is the Carbon Cycle Intercomparison Project, one is the Paleoclimate, PMIP, one is for the cloud feedback assessment, and so on and so forth. So this is another way that we have of trying to probe the uncertainty in our future predictions of climate. I have 2 minutes to tell you what we know, okay, about anthropogenic climate change. So I think when I boiled it down in my as I was cogitating about this last week, I thought there were 2 key observations that we have over the past century, which are critical as to driving our basic understanding of climate change. One is that the greenhouse gases have increased since pre-industrial times. Pre-industrial being defined as approximately 1750, and this increase in the greenhouse gases is due to human activity. What Linda showed was the Keeling curve for CO2, but there are similar curves for other greenhouse gases. And there are ways of trying to assess, basically using isotopes of carbon 12, 13, and 14 to assess where did the carbon come from. That tells us that the CO2 increase had to have come from the fossil fuels. The other key observation is that surface temperatures have risen since over the last century and before, and it's been globally, but also it's been locally, and I'll show you a picture of that. Plus, we have multiple observational records now that are consistent with these changes. The first 2 being the ones that have driven our science for the past probably 50 plus years. So globally, I'll skip the Keeling curve and jump right to number 2. Globally, surface temperatures have increased. Here is the picture from the latest IPCC report and the summary for policymakers. This is showing the decadal averages since 1850 up to the present. So it includes the last decade from 2000 to 2010. And what we see is the summary statement from the IPCC is that each of these, the last 3 decades, has been successively warmer than any preceding decade since 1850. And I think with the multiple data sets that we have, the multiple ways of looking at the data, not only globally, we can look at this spatially across the globe. This is one realization of the observed changes since from 1901 to 2012. These are estimates of the trend in the individual locations. Purple is bad, blue is good, if you want to look at warming as being bad. But we see globally the Earth has been warming everywhere at about 1 degree over the Celsius over the past century, and a few places have cooled, and a few places have warmed even more than that, up over 1.75 degrees over that 112-year period. These other lines of evidence, I'll skip over these a little bit, but we look at observed precipitation changes. As you can see, it's a much sparser network. It has much less of a signal than the temperature does. But when you look at the consistency between the precipitation changes with the temperature changes, we get a much better picture as to how the changes that are observed in precipitation are consistent with the warming that's been induced by the anthropogenic forcings. Other lines of evidence are snow cover. That's the upper left. The changes in Arctic sea ice extent are shown in the bottom left. Global average ocean heat content is shown in the upper right, and global average sea level change is shown in the bottom right. Again, since the start of the records, we can see that we have decreasing snow cover, decreasing sea ice extent, increasing heat content, increasing sea level change. Excuse me. And we also see that there's uncertainty about each of these records. And so we see the sort of 5 to 95 percentile bounds showing the ranges of the changes over these the past century. The last one is that we have a basic understanding of the fundamental science that's driving the climate change. And so the fundamental science states that changes in the greenhouse gases are disrupting the planet's energy balance. For those of you in the science community, that's probably very straightforward. And in order to understand how the Earth is going to be warming into the future, we have to understand how the warming of the past can be explained by the various forcing factors. But the basic premise here is that the climate system responds by adjusting to this imbalance. And as you saw in the picture of temperature change, it's not uniform. We have higher warming, larger warming in the Arctic regions compared to the tropics, and it's not uniform from land versus ocean. And ultimately, this basic premise is what's encoded into the climate models. We see the greenhouse gases increasing. We know that some of that heat is now being trapped on the planet, but then the climate system is going to be responding to this imbalance as a result. So are the models predicting the past? Excuse me. The answer is yes. These are the results from the Summary for Policymakers again. On the left is the change in land surface. Observations are shown in black. The models that use both the natural and anthropogenic forcings to look at the changes over the past century are shown as a pink swath, and that's representing the model uncertainty, this multiple model uncertainty that I was talking about earlier. The blue swath on the bottom is showing the models that only use natural forcings, so only volcanoes, changes in the sun's output, and a few other natural forcings. And what we see is that the observations are matching those which are shown, the models which are using both the natural and anthropogenic forcings, both over the land, over the combined land and ocean at the surface, and also the ocean heat content data that we're looking at, which is where approximately 90% or more of the energy is being absorbed is being observed in the planetary climate records. We can also look at this regionally, and I urge you to look at the Summary for Policymakers to look at this figure more closely. We look at it from the various continents, but we also look at the sea ice changes now, and we see that the trends in the sea ice change in the Arctic and Antarctic are more consistent with the anthropogenically forced cases. How many minutes do I have left? Negative? -5, okay. And then the other one is the ocean heat content. We can look at the various oceans, we can look at the land, we can look at the sea ice, and we see that there's this consistency between the climate models which are being used to predict the future with albeit a large amount of uncertainty, but they are showing the right response to the anthropogenic and natural forcings over the 20th century. And now I'm going to pass this on to Haley, because she's going to start talking about climate change impacts, and I'll stop there.